The entire cosmic story we know is built on a single, unimaginably brief moment. In the first microsecond of the universe, everything that defines our reality was forged. This is not the moment of the Big Bang's explosive birth, but the critical era that followed, an epoch far more ancient than the first stars or even the first atoms. It was a time of extreme transformation, where the fundamental forces of nature split apart and the very particles that make up you and me were created from a seething primordial soup. Understanding this fleeting instant is the key to unlocking the deepest secrets of physics, from why matter exists at all to the grand architecture of the cosmos. By the end of this journey, you will see the universe not as a static stage, but as a dynamic story whose first lines were written in a fraction of a blink. How did a perfectly symmetrical beginning give rise to the flawed, structured, and life-friendly cosmos we inhabit today? What does it mean that our entire existence hinges on events too brief for any clock to measure? This first microsecond is a defined and crucial slice of time. It is the period from the very instant of the Big Bang, which we call time zero, to 1/1,000,000th of a second later. To grasp how ancient this is, we must stretch our minds across the cosmic calendar. The first stable atoms, the building blocks of all ordinary matter, did not form until about 380,000 years after the Big Bang. The first stars ignited millions of years after that, so this microsecond is not merely early, it is profoundly, almost incomprehensibly primordial. It exists in an epoch before anything we would recognize as a physical object could form. We cannot point a telescope back to see it, as the universe was still opaque, a dense fog of energy. Instead, our window into this era comes from two powerful tools: the elegant equations of theoretical physics and the monumental machines we have built here on Earth. Giant particle colliders like the Large Hadron Collider slam particles together at nearly the speed of light, recreating for a fleeting instant the unimaginable energies and temperatures that filled the universe during that first microsecond. In a very real sense, these experiments are time machines, allowing us to run the cosmic film in reverse and witness the conditions from which everything emerged. To truly understand that first microsecond, we must begin at the very edge of understanding, a moment so brief it defies ordinary description. This is the Planck epoch, the span from the instant of creation to 10 to the power of -43 seconds. At this scale, the universe was smaller than a single atom, and the energy density was so immense that the very fabric of reality as we know it unravels. Our trusted tools, Einstein's theory of gravity and the quantum laws of particle physics, ceased to function. In this realm, the familiar concepts of space and time themselves may not have existed in any recognizable form. It is a frontier where physics meets philosophy, a blank slate upon which the first laws of the cosmos were perhaps written. Theories like string theory or loop quantum gravity attempt to sketch a picture of this era, suggesting a frothing quantum foam or a dance of vibrating strings where space and time are emergent properties, not a fixed stage. While these ideas are profound, they remain largely in the domain of mathematical exploration. For our story, the Planck epoch represents the ultimate horizon of knowledge, a reminder that our cosmic narrative has a first page we cannot yet fully read. But as we move forward from that absolute zero point, even by an unimaginably tiny fraction of a second, the fog begins to lift, and the universe takes its first tentative steps toward becoming something we can begin to comprehend. As we move forward from that impossible beginning, the universe enters its first recognizable phase of existence. From 10 to the power of -43 seconds to about 10 to the power of -36 seconds, the cosmos was a realm of unimaginable heat and density, yet it was beginning to play by rules we can start to describe. This is known as the Grand Unification Epoch, and its central idea is one of profound simplicity. In this furnace of creation, 3 of the 4 fundamental forces we know today were not separate entities at all. The strong nuclear force which binds atomic nuclei together, the weak nuclear force responsible for certain types of radioactive decay, and the electromagnetic force which governs light and chemistry, were all fused into one single, unified superforce. Gravity, the most familiar force to us, had already split away at the end of the prior Planck epoch, leaving these 3 to rule this early era in perfect harmony. The theoretical framework that attempts to describe this unified state is called a grand unified theory, or GUT. Think of it like this: imagine you have a specialized toolkit. You have a wrench for bolts, a screwdriver for screws, and a hammer for nails. They are distinct tools for distinct jobs, but if you could heat that toolkit to an impossibly high energy, the metal would melt into a single, glowing pool of liquid. In that state, the distinctions between wrench, screwdriver, and hammer vanish. They are all just one substance. A grand unified theory suggests that in the extreme energy of the early universe, the forces we see as separate today were like those distinct tools, all melted into one fundamental, symmetric substance. This epoch is absolutely critical to our story because it represents the universe in its most symmetric, most orderly, and most mathematically beautiful state. Everything was governed by one set of elegant rules. The cosmos was uniform, balanced, and simple. Yet, as we will see, this perfect symmetry was destined to be broken. The story of our universe, and indeed our own existence, hinges on what happened when this pristine unity began to crack, setting the stage for everything that was to come. This perfect symmetry could not last. By the time the universe reached 10 to the power of -36 seconds, the cosmos was still smaller than a single proton, but it was cooling rapidly as it expanded. Within that seething, energetic soup, a subtle instability was brewing. Physicists proposed that all of space was filled with a new and peculiar kind of energy, a hypothetical entity known as a scalar field. We can think of a field as an invisible condition or a property that exists everywhere, like a temperature map or a magnetic influence. This specific field, often called the Inflaton field, held the universe in a precarious state. Imagine a ball resting at the very top of a perfectly rounded hill. This position is possible, but it is unstable, a state of high potential energy. The slightest nudge will send it rolling down. The Inflaton field was in a similar condition, known as a false vacuum. It was not the true, lowest energy state of the cosmos, but a temporary, high-energy plateau. The universe was trapped in this tense, energetic configuration, brimming with a potential that was about to be unleashed in the most dramatic transformation since the beginning of time. Then the universe took a breath and stretched. Around 10 to the power of -36 seconds, that unstable Inflaton field finally tipped over the edge. It decayed, rolling down its energy hill to a more stable, lower state. But this was not a gentle settling. The energy released from this transition was staggering, and it was injected directly into the fabric of space itself. The result was a phenomenon so extreme it seems to defy the laws of physics, cosmic inflation. For a fleeting sliver of time, from about 10 to the power of -36 to 10 to the power of -32 seconds, the universe underwent exponential expansion. Space did not just grow, it exploded in scale, inflating by a factor of at least 10 to the power of 26. To grasp that number, picture a single atom. Now imagine that atom swelling to become larger than our entire observable universe today, all in a time span so brief it makes a microsecond feel like an eternity. This expansion happened faster than the speed of light, which is permissible because it was space itself stretching, not objects moving through space. The consequences of this violent growth spurt were absolutely fundamental. First, it ironed out the cosmos. Any initial wrinkles, lumps, or irregularities in the energy density were stretched so thin that the universe became incredibly smooth and flat on large scales, just as blowing up a balloon smooths out the creases in the rubber. Second, and most miraculously, inflation did not create perfect silence. The quantum foam that permeated that tiny, early universe was full of tiny, random fluctuations, brief pops of energy appearing and disappearing. As space inflated at a mind-boggling rate, it stretched these microscopic quantum jitters along with it, freezing them into the fabric of reality and magnifying them to cosmic proportions. Those frozen ripples in density became the gravitational seeds for everything to come, the subtle blueprints for all future galaxies, stars, and planets. By the time inflation ended, around 10 to the power of -32 seconds, the stage was set. The universe was vast, smooth, flat, and imprinted with the faint, primordial fingerprints of structure. The era of perfect symmetry was over, and the cosmos was now primed for the next, equally dramatic act of creation. But with the end of inflation came a new beginning. The immense energy that had been driving the expansion of space did not simply vanish. It was released in a sudden, spectacular cascade, a process physicists call reheating. As the Inflaton field settled into its stable state, it decayed, shaking off its stored energy like a great cosmic bell ringing out. This energy flooded the newly stretched emptiness of the universe, filling it with an intense, searing heat and a frenzied swarm of the most fundamental particles and forces. In a very real sense, this was the moment the hot Big Bang truly began. The universe was effectively reset, not from nothing, but from a cold, stretched void into a blisteringly hot, unimaginably dense soup of pure energy and potential. This was the birth of the primordial Quark-Gluon Plasma. Quarks are the fundamental building blocks of particles like protons and neutrons, and gluons are the force carriers that bind them together. But in this plasma, the energy was so extreme that quarks and gluons could not stick together at all. They existed in a free-flowing, chaotic state, like individual ingredients in a cosmic broth too hot to ever form a solid meal. For the first time, the universe was filled not with a mysterious field, but with the raw, churning material from which every single atom in your body, every star, and every galaxy would eventually be forged. This was the starting material, the ultimate cosmic ore, and its properties would dictate the fate of everything. This primordial broth was a state of matter unlike anything in our present universe. For the next few microseconds, the cosmos was a seething, opaque sea known as the Quark-Gluon Plasma. In this extreme environment, the fundamental quarks and the gluons that bind them were not confined inside familiar particles like protons and neutrons. They roamed freely, a dense soup of unbound ingredients constantly colliding and interacting. The temperature was an almost incomprehensible several trillion degrees, and the density was so immense that a teaspoon of this plasma would outweigh a mountain. This was not a calm, simmering liquid, but a chaotic, churning medium where the very rules of confinement were suspended by the sheer, overwhelming energy of the young cosmos. The universe was completely opaque during this time, a brilliant, impenetrable fog. Light particles or photons could not travel any meaningful distance before being absorbed and re-emitted by this frenetic sea of quarks and gluons. For all intents and purposes, the universe was a blindingly bright prison with no visibility, its internal workings hidden behind a wall of pure energy. This plasma represents a critical chapter in our story, the direct precursor to all the structured matter that would follow. And remarkably, this chapter is not locked in the distant past. Scientists have successfully recreated tiny, fleeting samples of the Quark-Gluon Plasma right here on Earth. In massive particle colliders like the relativistic heavy ion collider and the Large Hadron Collider, they slam heavy atomic nuclei together at velocities approaching the speed of light. These collisions concentrate an enormous amount of energy into a microscopic space, briefly heating a pinpoint region to temperatures over 100,000 times hotter than the Sun's core. For a mere fraction of a second, the protons and neutrons in those nuclei melt, their constituent quarks and gluons liberated into a tiny fireball that mimics the conditions of the early universe. By studying the debris and signals from these miniature cosmic recreations, physicists gain direct experimental insight into the behavior and properties of that first searing microsecond, transforming theoretical speculation into observable, measurable science. But that brilliant, chaotic soup could not remain free forever. The universe was expanding relentlessly, and with that expansion came cooling. As the temperature plummeted below about 2 trillion Kelvin, a profound and permanent change swept across the cosmos. The strong nuclear force, one of the fundamental forces that had been unified with the others in that earlier epoch of perfect symmetry, finally froze out. It crystallized into its own distinct identity, forever separating from the still unified electroweak force. This was not a violent event, but a subtle shift in the very conditions of reality, like water turning to ice as the temperature drops. In the searing heat of the Quark-Gluon Plasma, the strong force was effectively switched off, allowing quarks and gluons to flit about independently. But once the temperature fell below that critical threshold, the force between them suddenly became active and overwhelmingly powerful. It was as if an invisible glue, previously melted and ineffective, had instantly solidified. Quarks could no longer roam free. The moment they tried to stray even a tiny distance from one another, the force between them yanked them back with irresistible strength. This is called confinement, and it marks the moment the first stable particles of matter were forged from the primordial fire. Pairs and triplets of quarks, bound tightly by gluons, snapped together to form the very first protons and neutrons, the permanent building blocks of atomic nuclei. In a flash, the universe transitioned from a formless, seething plasma into a slightly more structured, though still incredibly dense and hot, soup of hadrons. The strong force had drawn its first permanent lines in the cosmos, creating the enduring architecture for all the solid matter that would one day follow. The universe had just passed its most violent growth spurt and was now cooling rapidly. This cooling triggered a fundamental change in the very rules of matter. Around 10 to 100 microseconds after the beginning, the temperature fell below a critical threshold of about 2 trillion Kelvin. At this moment, the universe underwent a phase transition as profound as water freezing into ice. In the prior Quark-Gluon Plasma, quarks and gluons were like individual water molecules in a superheated liquid, moving about independently with tremendous energy. But as the cosmic temperature dropped, the strong nuclear force, which had been latent in the extreme heat, suddenly became the dominant power in the universe. It was as if the liquid had reached the freezing point, and the molecules began locking into a rigid, crystalline structure. This process is called hadronization. The free quarks, which simply cannot exist in isolation under normal conditions, were forcefully and permanently bound together by gluons. Triplets of quarks snapped together to form protons and neutrons, the heavy particles collectively known as hadrons. At the same time, quark-antiquark pairs combined to form lighter, unstable hadrons called mesons. In a cosmic instant, the formless, seething plasma of free ingredients solidified into the first stable seeds of matter. This was not a gentle coalescence, but a mandatory confinement, a fundamental shift in the state of the cosmos that created the permanent building blocks for everything to come. For every proton forged, an antiproton was also created, and for every neutron, an antineutron. The universe was now a dense, hot soup of matter and antimatter particles, constantly colliding and annihilating each other back into pure energy in a furious, balanced dance. This delicate and dangerous equilibrium, however, was about to be tipped by the most important accident in cosmic history. That furious dance of matter and antimatter held a terrifying possibility. If the universe had remained perfectly balanced, every particle of matter would have eventually met its antimatter twin, annihilating in a flash of energy and leaving behind a cosmos of nothing but cold, empty light. The very existence of galaxies, planets, and life hinges on a single, crucial fact: that this perfect symmetry was broken. Somehow, during these earliest moments, a tiny, almost imperceptible preference for matter over antimatter was baked into the laws of the cosmos. This is the mystery of baryogenesis, the genesis of matter's dominance, and its roots lie in the events unfolding just as the first protons and neutrons were forming. In that seething hadron soup, for every billion quark and antiquark pairs that annihilated each other, one extra quark was left behind, 1 in a billion. It seems like a negligible amount, a rounding error in the grand equation of creation. Yet that minuscule surplus, that one lonely quark for every billion annihilations, is the reason anything substantial exists at all. Every atom in your body, every star in the night sky, is made from the remnants of that 1 in a billion advantage. The question is, what cosmic rule could have favored matter so slightly, yet so decisively? For such an asymmetry to occur, the physics of the early universe had to violate some very deep-seated symmetries that physicists once believed were unbreakable. The leading framework to explain this involves 3 conditions that had to be met. First, there needed to be processes that did not conserve baryon number, meaning the total amount of matter could actually change. Second, the laws of physics had to treat matter and antimatter slightly differently, violating what is called charge parity symmetry, or CP symmetry. Think of it like a perfectly mirrored dance. If you film a particle interaction and then play the film in reverse while also swapping every particle with its antiparticle, a CP symmetric universe would look exactly the same. Our universe does not. The third condition required these processes to occur out of thermal equilibrium, meaning the universe was changing faster than the particles could react and rebalance the scales. Remarkably, the standard model of particle physics contains all the ingredients for these conditions, but in amounts far too small to account for the vast amount of matter we see. The tiny CP violation we have observed in particle accelerators is insufficient by many orders of magnitude. This tells us that the true source of matter's dominance must involve physics beyond our current model, processes that were most active in the Electroweak era that followed this first microsecond. The breaking of the unified electroweak force, a pivotal event just after our time frame, likely created the perfect storm, a moment of dramatic change where these subtle biases could be amplified and frozen into the fabric of reality. So while the Quark-Gluon Plasma gave us the building blocks, it was the instance that followed that decided their fate, tipping the scales from a potential void of pure light toward a universe rich with structure and possibility. The universe had just crossed a critical threshold, its first stable particles now forged from the cooling fire, but the cosmos was far from settled. As the temperature continued to plummet, the universe entered a new and pivotal era known as the Electroweak Epoch. This period, spanning from the end of hadronization up until about 10 to the power of -12 seconds, was defined by a powerful and elegant unity. 2 of the 4 fundamental forces, the electromagnetic force and the weak nuclear force, were still fused together as a single, coherent entity. To understand the significance of this, think of electricity and magnetism. For centuries, they were considered separate phenomena, but we now know they are 2 faces of a single electromagnetic force, a revelation that powers our modern world. The Electroweak Epoch represents an even deeper unification, a time when the force responsible for light and chemistry was intrinsically linked with the force governing certain types of radioactive decay. In this hot, dense universe, there was no distinction between them. They were different manifestations of one underlying electroweak force. This perfect symmetry was maintained by the particles that carried its influence. Today, we know the carrier of the electromagnetic force as the photon, a massless particle of light that zips across the cosmos at, well, the speed of light. But in that early, energetic soup, the photon was not alone. It was accompanied by three heavy siblings, the W+, W-, and Z0 bosons. These are the carriers of the weak nuclear force. In our cold, modern universe, these W and Z bosons are incredibly massive, about 100 times the mass of a proton. This heft means they are very short-lived and can only act over subatomic distances, which is why the weak force has such a limited range. But during the Electroweak Epoch, the temperature was still so phenomenally high, around 10 to the power of 15 degrees, that energy was abundant. In this environment, mass became almost irrelevant. The colossal energy of the cosmic broth could easily create these massive particles spontaneously, and they roamed freely alongside photons. From the perspective of the particles swirling in that soup, there was no practical difference between interacting via a photon or a W or Z boson. The symmetry was unbroken. The universe was a place where the forces of light and radioactivity were one and the same, a unified field where the massive and the massless were indistinguishable. This state of perfect electroweak symmetry was the last great unification before the cosmos cooled enough to write its final, permanent set of rules, setting the stage for the next and perhaps most transformative break of all. This perfect electroweak symmetry could not survive the universe's relentless expansion and cooling. As the cosmic temperature dipped below a critical threshold, roughly 10 to the power of 15 degrees, the universe underwent one of its most important transformations, a phase transition known as electroweak symmetry breaking. To grasp this, we must understand a field that permeates all of space, the Higgs field. In the extreme heat of the earlier universe, this field had an average value of 0. Imagine a ball resting in the center of a wide, flat plateau, able to roll in any direction with equal ease. This represents the symmetric state, where the electromagnetic and weak forces were indistinguishable. But as the cosmos cooled, the shape of this energy landscape changed dramatically. The flat plateau developed a dip in its center, surrounded by a circular valley. The ball, representing the state of the Higgs field, could no longer stay at the 0 point. It naturally rolled down into the valley, settling at a new, stable, non-zero value. This was not a random fall. It was the universe finding a new, lower energy state. The moment the Higgs field acquired this universal value, symmetry was broken. The consequences were immediate and profound for every particle in the cosmos. The once massless W and Z bosons, the carriers of the weak force, now had to move through this newly established Higgs field. Their interaction with it is what endowed them with their characteristic heavy mass, making them sluggish and short-ranged. The photon, however, did not interact with the Higgs field at all. It remained massless and could travel at the speed of light forever. In that single instant, the unified electroweak force cleaved permanently into two distinct forces, the short-range weak nuclear force and the long-range electromagnetic force. But the influence did not stop there. Fundamental particles like quarks and electrons also gained their mass by interacting with this omnipresent field. The universe was no longer a place of perfect, weightless symmetry. It became a structured arena with differentiated forces and particles possessing tangible substance. This breaking of symmetry, a direct result of cooling from the unimaginable conditions of the first microsecond, is why matter has heft and why the forces of nature operate as they do. It transformed a uniform, energetic soup into a cosmos with the specific rules necessary for complexity and, ultimately, for us. Amidst that churning soup of quarks and gluons, another, far more elusive actor played a vital role. Neutrinos, the ghostly particles that barely interact with anything, were everywhere. Today, trillions of them pass through your body every second without a trace. But in the first microsecond, the universe was so unimaginably dense that even these phantoms could not escape. They were trapped in constant, frantic collisions with the surrounding sea of particles, locked in a state physicists call thermal equilibrium. This means the neutrinos were exchanging energy freely with the quarks, gluons, and electrons, acting as a crucial component of the cosmic broth's internal pressure and helping to shape its dynamic behavior. They were an integral part of the plasma's thermodynamics, influencing how it expanded and cooled. This intimate entanglement, however, was destined to be short-lived. As the universe continued to expand and thin out, the rate of these collisions began to drop. Roughly 1 second after the Big Bang, a pivotal moment arrived, the neutrino decoupling. The density of matter had fallen so low that neutrinos could finally travel vast distances without bumping into anything. They effectively stopped interacting with the rest of the cosmos and streamed freely into the growing void, becoming a permanent, invisible background sea. This cosmic neutrino background still permeates the entire universe today, a fossil relic carrying a pristine snapshot of the universe as it was just 1 second old. While we have not yet directly detected this specific neutrino background, its existence is a firm prediction of our standard model of cosmology. Finding it would be like uncovering a photograph from the universe's infancy, offering a direct glimpse into conditions moments after the primordial fire had cooled, a silent echo of that first transformative microsecond. Theoretical models give us a breathtaking narrative, but science demands proof. That proof comes not from telescopes, but from colossal machines buried deep underground. Beneath the border of France and Switzerland, the Large Hadron Collider is a 27-kilometer ring of supercooled magnets. At the Brookhaven National Laboratory in New York, the relativistic heavy ion collider performs a similar, specialized task. These are not just particle accelerators, they are the most precise time machines ever built. They do not look into the past, they recreate it. By stripping atoms of their electrons and accelerating the bare, heavy nuclei of elements like lead or gold to over 99.99% the speed of light, scientists create conditions not seen since the universe was a mere microsecond old. When these two microscopic specks of matter, each containing hundreds of protons and neutrons, are sent on a head-on collision course, something extraordinary happens. In the instant they meet, the energy of their motion is concentrated into a space smaller than a single atomic nucleus. The temperature in that pinpoint region soars to over 5 trillion degrees, more than 100,000 times hotter than the core of our Sun. For a fleeting moment, measured in mere yoctosecons, the protons and neutrons within those nuclei cease to exist. They melt. Their constituent quarks and gluons, normally locked tight by the strong force, are liberated into a seething, minuscule fireball of Quark-Gluon Plasma. For that briefest of instants, a piece of the early universe flickers back into existence right before our detectors. The plasma exists for less than a billionth of a second before it expands, cools, and the quarks and gluons recombine into a shower of thousands of new particles. But in that sliver of time, sensitive instruments capture everything. They measure the plasma's temperature, its density, how it flows like a nearly perfect liquid with almost zero viscosity, and how it transmits energy. Each collision is a miniature, controlled recreation of the primordial fire, and the data streaming out validates and refines our theoretical models of that first microsecond. What was once a speculative story written in mathematics is now an observable, measurable phenomenon. We are not just imagining the birth of matter, we are watching it happen, one ultra-high energy collision at a time. These cosmic collisions provide a direct, laboratory-scale glimpse into the primordial fire, but the most powerful evidence for our story is written across the entire sky, in the oldest light in the universe. This is the cosmic microwave background, a faint, cold glow that fills every direction of space. It is the afterglow of the Big Bang itself, released when the universe was just 380,000 years old and finally became transparent. While that moment came long after our first microsecond, the pattern of this ancient light carries the indelible fingerprints of that earlier, more violent epoch. The CMB is incredibly uniform, varying in temperature by only tiny fractions of a degree. This remarkable smoothness is a direct prediction of cosmic inflation, which stretched the infant cosmos to erase any major irregularities. But it is not perfectly smooth. Scattered across this cosmic canvas are minute, patchy variations in temperature, like a subtle texture on an otherwise smooth sheet. These are not random noise. They are the magnified and frozen imprints of those microscopic quantum fluctuations that were born in the first instant and stretched to cosmic proportions during inflation. The specific pattern of these hot and cold spots, their size, distribution, and statistical properties, matches the predictions of inflationary theory with stunning precision. It tells us that the seeds for all cosmic structure, from the largest galaxy clusters to the voids between them, were sown in that unimaginably brief period of hyper-expansion. Furthermore, the CMB light is polarized, meaning its waves vibrate in preferred directions. This polarization carries a specific pattern, like a swirl or a curl, known as B-modes. Certain patterns of B-mode polarization are a unique predicted signature of primordial gravitational waves, ripples in spacetime itself that would have been generated by the violent energy of the inflationary field. While the search for this definitive signal is ongoing, the existing data from the CMB on temperature and other polarization patterns provides overwhelming, indirect evidence that the inflationary scenario and the conditions of extreme energy and rapid change it describes is the most accurate picture we have of the universe's first moments. In a very real sense, when we look at a map of the cosmic microwave background, we are looking at a baby picture of the cosmos that was developed from a negative exposed during the first microsecond. The grand cosmic web we see today, a vast network of galaxies strung along filaments with immense voids in between, did not appear by accident. Its blueprint was drawn in those first moments. Those microscopic quantum ripples, frozen into the fabric of the universe during inflation and imprinted on the cosmic microwave background, were more than just temperature differences. They were the seeds of all future structure. Where the density was slightly higher than average, gravity had a tiny head start. Over hundreds of millions of years, that extra gravitational pull began to draw in surrounding dark matter and gas, a slow, relentless process of accumulation. Think of it like a gentle slope on a perfectly flat plane. Water will naturally begin to flow toward that subtle depression, and over time it carves a deeper and deeper channel. In the cosmos, the initial density variations were those gentle slopes, and gravity was the water, flowing toward them and amplifying them over cosmic time. The regions that started with a slight overdensity became the hubs, the future sites of galaxy clusters. The underdense regions expanded into the great cosmic voids. This gravitational processing is why the large-scale structure of the universe is not random. It follows a specific statistical pattern, a cosmic fingerprint. When astronomers map the positions of millions of galaxies, they are not just making a picture, they are reading a fossil record. The statistical properties of this web, the sizes of clusters, the distances between filaments, even the way galaxies are grouped, all contain encoded information about the initial conditions from which they grew. It is a direct link between the quantum jitters of the first microsecond and the majestic architecture of the present-day universe. By studying this fossil, we can test our theories of inflation backward, asking if the pattern we see in the galaxies matches the pattern predicted by the quantum fluctuations from the dawn of time. While the cosmic blueprint for visible matter was being drawn, another, far more massive component of the cosmos was likely taking shape in the shadows. This is the profound mystery of dark matter production. We know dark matter exists because of its gravitational pull on galaxies and the large-scale structure of the universe, yet it remains invisible, not interacting with light or ordinary matter in any way we have yet detected. Its origin is one of the greatest puzzles in physics, and many leading theories point directly back to the extreme conditions of the universe's first microsecond. The leading candidate for dark matter for decades has been a hypothetical particle known as a weakly interacting massive particle, or a WIMP. The beauty of this idea lies in its elegant connection to early universe physics. In the searing heat of the primordial plasma, WIMP would have been produced in great abundance, constantly colliding with each other and with particles of ordinary matter. They would have been in thermal equilibrium, part of that churning cosmic soup, but as the universe expanded and cooled, a pivotal moment would have arrived. The temperature would have dropped below the mass energy of the WIMP particle itself. At that point, the typical energy of collisions in the cosmic broth would have become too low to create new WIMP pairs. Even more critically, the expanding universe would have become too diffuse for the existing WIMP to find each other and annihilate. In a cosmic instant, they would have frozen out of thermal equilibrium. Their population would have been fixed, left behind as a relic population that simply could not interact enough to disappear. Remarkably, if you calculate the expected abundance of such frozen-out particles based on the known expansion rate and temperature of the early universe, you get a number that aligns stunningly well with the amount of dark matter we observe today. This is known as the WIMP miracle, and it suggests that dark matter could be a natural byproduct of the same hot, dense conditions that forged protons and neutrons. While WIMP are not the only candidate, this compelling link makes the first microsecond a prime suspect for the era when the invisible scaffolding of the cosmos was forged. The search to identify dark matter, therefore, is not just a hunt for a hidden particle. It is an archaeological dig into the universe's first moments, seeking the frozen relics of a time when everything was energy and the rules of reality were being written. Yet the theory of cosmic inflation was not born from pure imagination. It emerged as a brilliant and necessary solution to two profound puzzles that plagued our understanding of the Big Bang, mysteries so deep they threatened to undermine the entire story. The first is called the horizon problem. When we look at the cosmic microwave background, the ancient light from opposite sides of the sky, we find something astonishing. Those regions, now billions of light years apart, have almost exactly the same temperature to within 1 part in 100,000. According to the standard Big Bang model without inflation, this makes no sense. Those two patches of sky were so far apart when the CMB was released that light, traveling at the universe's speed limit, would not have had nearly enough time to travel between them. They were outside each other's cosmic horizon, forever out of causal contact. Think of two people standing in a vast, dark field, each holding a lantern. If the field is too wide, the light from one lantern can never reach the other person's eyes. They have no way to coordinate or agree on anything. In the old Big Bang model, distant regions of the universe were like those isolated people. They could never have exchanged heat or information to reach a common temperature, so how did they manage to synchronize their conditions so perfectly? The second puzzle is the flatness problem. The geometry of our universe, as best we can measure, is incredibly flat. Not flat like a table, but flat in the sense of Euclidean geometry, where parallel lines never meet and the angles of a triangle add up to exactly 180 degrees. General relativity tells us that the density of matter and energy in the universe determines its curvature. There is a critical density that marks the precise balance between a universe that eventually collapses in on itself and one that expands forever into a thin, cold void. Our universe's actual density is astonishingly close to that critical value. For it to be so perfectly flat today, some 13.8 billion years after the Big Bang, its density in the earliest moments must have been fine-tuned to 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros, a precision so unimaginable it would be like balancing a pencil on its tip for billions of years. The old model offered no explanation for this miraculous razor's edge balance. These were not minor curiosities. The horizon problem and the flatness problem were glaring logical flaws in the narrative of a simple, hot, expanding universe. Then came the idea of inflation. This period of hyper-rapid expansion in the first fraction of a microsecond provided an elegant, single solution to both. It solved the horizon problem because before inflation, the entire observable universe was once crammed into a tiny, subatomic region that was in perfect thermal contact. Every part of it was cozy and connected. Then, inflation stretched this tiny, uniform region to a size larger than our entire observable cosmos. The regions that now appear impossibly distant were once neighbors, able to easily share heat and reach equilibrium. Inflation then pushed them far apart, faster than light could connect them again, freezing that uniformity into place. It solved the flatness problem by acting like a cosmic magnifying glass on the geometry of space. Imagine the surface of a balloon. If you inflate it from a tiny speck to the size of a house, any small wrinkle or curvature on its original surface becomes stretched so thin that a tiny patch of it appears perfectly flat to an ant walking on it. Inflation did exactly this to the fabric of space-time. No matter what the initial curvature of the infant universe was, inflating it by a factor of 10 to the 26 would force it to appear flat within our observable horizon. The theory did not require a miraculous fine-tuning of initial conditions. It produced a flat universe as a natural outcome of its explosive growth. In this way, the puzzles that once seemed to break our cosmic story became the very evidence for its most dramatic opening chapter, a testament to the transformative power of that first, fleeting fraction of a microsecond. This link between the quantum realm and the cosmos is perhaps the most astonishing idea in all of modern cosmology. In the very first instant, the universe was so incredibly tiny that the bizarre rules of quantum mechanics governed everything. One of the foundational principles of this quantum world is a constant, inherent uncertainty. Empty space is never truly empty. It is a seething, bubbling sea of potential. At scales smaller than an atom, particles and their antiparticles can spontaneously wink into existence, borrowing energy from the vacuum for a fleeting moment before annihilating and returning it. This is not just theoretical. We see its effects in precise laboratory experiments. In that primordial moment, the Inflaton field, the energy driving the universe's hyper-expansion, was subject to this same quantum jitter. Its value at any one point in that tiny, pre-inflationary universe was not a fixed number. It danced with a tiny, unpredictable fluctuation. Think of the surface of a perfectly calm pond on a windless day. Even in that stillness, if you look closely, you see a faint, ever-present shimmer, a result of countless tiny vibrations at the molecular level. The Inflaton field had a similar quantum shimmer, an intrinsic fuzziness written into the fabric of reality itself. These were not imperfections. They were the natural, humming background noise of existence at the smallest scales. Under normal circumstances, such quantum fluctuations are fleeting and microscopic, vanishing almost as soon as they appear, utterly insignificant to the larger world. But the universe was about to perform a magic trick of unimaginable scale. When cosmic inflation began, it did not just stretch space. It stretched everything in it, including those immeasurably tiny quantum ripples in the Inflaton field. As space expanded exponentially, those submicroscopic wrinkles were pulled and magnified across light years, then across billions of light years. the quantum shimmer was frozen into the geometry of the cosmos itself, transformed from a fleeting whisper at the Planck scale into a permanent imprint on the universe. Where the Inflaton field had a slightly higher value due to a quantum fluctuation, inflation lasted a fraction longer, releasing a bit more energy as it ended. This created a region of space with a slightly higher density of matter and energy. Where the field had a slightly lower value, a region ended up slightly less dense. In this way, the perfect quantum randomness of the microscopic world was transcribed by inflation's relentless stretching into a pattern of minuscule density differences across the entire observable universe. These differences were tiny, perhaps only 1 part in 100,000, but they were now etched onto a cosmic canvas. Gravity, always attentive to density, saw these subtle variations as a blueprint. Over the next billions of years, it would patiently pull matter toward the slightly denser regions, building the great cosmic web of galaxies and voids we see today. The majestic architecture of the universe, with its glittering galaxies and vast dark expanses, began as quantum static, a hum of uncertainty amplified to a cosmic symphony. Your existence and the existence of every star you see is a direct consequence of that quantum fuzziness, stretched and frozen into the very bones of reality during the first fraction of a microsecond. Yet that entire story unfolded under a single, overarching rule. The first microsecond was not just a brief moment, it was the opening act of a much longer epoch, a time when the universe was governed by light. This was the radiation-dominated era, and it lasted for roughly 47,000 years. To understand its significance, picture the cosmos as a contest for control over its own expansion. In this contest, the competitor with the highest energy density calls the shots, dictating how fast space stretches. For nearly all of its first microsecond, and for millennia afterward, the undisputed champion was radiation. This term includes not just photons of light, but also the ultra-relativistic particles zipping around at nearly light speed, like those free quarks, gluons, and neutrinos in the primordial soup. Their collective energy was so immense that it completely overwhelmed the comparatively sluggish energy tied up in the mass of matter particles. The expansion of the universe during this time was therefore driven by the relentless pressure and energy density of this brilliant, chaotic sea of radiation. It was a cosmos ruled by light and speed, where the behavior of every particle and the very stretching of space itself were dictated by the physics of pure energy. This context is crucial because everything we have explored, from the breaking of symmetries to the formation of protons, happened under this specific regime. The particle physics of that first microsecond did more than just create building blocks. It set the initial conditions for this entire radiant era, determining how much of each particle would exist and how they would interact as the cosmos cooled. The eventual transition to a matter-dominated universe, the quiet shift that allowed gravity to slowly build galaxies from the seeds of those quantum ripples, was a direct consequence of decisions made in that first flash of time. The universe we inhabit today, with its dark skies and clustered galaxies, was born from an age of unimaginable light, an age whose fundamental rules were written before the first tick of a cosmic clock had even finished. This grand narrative is compelling, but it is not complete. Our journey into the first microsecond brings us face to face with the very edge of human understanding, where the map of known physics fades and the territory of deep mystery begins. The theoretical framework we have is incredibly successful, but it rests upon pillars we cannot yet see directly. For instance, the Inflaton field itself remains a hypothetical construct. While it perfectly explains the observed flatness and uniformity of the cosmos, we have no direct experimental evidence for its existence or its specific properties. What was it truly? Was it a single field or a complex interplay of many? the details of how it decayed and transferred its energy to the primordial plasma, the process called reheating, are also largely unknown. It is like knowing a great dam broke to fill a valley, but not understanding the precise mechanics of the spillway or the first turbulent moments of the flood. These are not minor gaps, they are central to the story of creation. Similarly, the beautiful idea of a grand unified theory where three forces become one remains an elegant mathematical aspiration. While the logic is powerful, no single theory has yet emerged that successfully merges the strong force with the electroweak force while making testable predictions that match our universe. The energy scales required to probe such unification directly are so astronomically high that they lie far beyond the reach of any particle collider we could ever conceivably build on Earth. Our most powerful machines recreate conditions from about 1 microsecond onward, but to peer further back into the RHIC epoch or the Planck instant requires energies 1 trillion times greater. This creates a fundamental horizon in our exploration. We are like historians trying to reconstruct the first minute of a civilization's history, but all written records begin an hour later. We must rely on the forensic traces left in the later universe, like the pattern of galaxies or the potential stability of protons, to infer what those first moments must have been like. These are not failures of science, but its defining challenges. They remind us that the cosmos still holds profound secrets, and that the story of the first microsecond, as detailed as it has become, is still being written with every new observation and every bold theoretical leap. These profound mysteries of the earliest moments push our theories into realms of breathtaking speculation. At the frontier of this exploration lies string theory, an attempt to weave gravity and quantum mechanics into a single, coherent tapestry of reality. In this framework, the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating strings. Their different vibrational patterns give rise to all the particles and forces we observe. For string theory to be mathematically consistent, it requires the universe to have more than the 3 spatial dimensions we experience, often proposing 10 or more. The extra dimensions are thought to be curled up or compactified at scales far smaller than an atom. This is where the story of the first microsecond becomes deeply intertwined with these cutting-edge ideas. The process of cosmic inflation, that brief period of hyper-expansion, finds a natural home within many string theory models. The Inflaton field, the engine of that expansion, could emerge from the dynamics of these strings and extra dimensions. More intriguingly, some string theory models suggest that the transition that ended inflation, when the Inflaton field rolled into its stable state, could have been accompanied by the settling of these extra dimensions into their final, compact shape. In this view, the geometry of our entire reality, the number of dimensions we perceive and the strengths of the fundamental forces, were crystallized during the same transformative events that defined the first microsecond. This paints a picture where the most basic rules of our cosmos were not preordained, but dynamically decided in the fiery aftermath of creation. This line of thinking leads to an even more staggering possibility, the multiverse. Some models of inflation, particularly those connected to string theory, suggest that inflation may not have been a one-time event that started and stopped everywhere. Instead, it could be eternal. In this scenario, the Inflaton field does not decay uniformly. Picture a pot of water coming to a boil. Most of the water transitions to bubbles of steam, but some pockets of liquid water remain. In eternal inflation, our entire observable universe might be just one bubble or pocket within a vast, eternally inflating meta-universe. In our bubble, the Inflaton field decayed, ending inflation and giving rise to our Big Bang and the universe we know. But outside our bubble, inflation continues at a mind-numbing rate, constantly giving birth to new, separate bubble universes. each with potentially different physical laws and constants determined by how their extra dimensions curled up. This is not science fiction, but a serious, though highly speculative, consequence of marrying inflationary cosmology with our best attempts at a theory of everything. It suggests that the specific conditions of our universe, the fine-tuned constants that allow for stars, planets, and life, might be the result of a cosmic lottery across a multiverse of possibilities. While these ideas are far from proven and may forever lie beyond direct observational test, they represent the ultimate extension of our quest to understand the first microsecond. They challenge us to consider that our entire cosmic story, from quantum ripples to galaxies, might be just one chapter in a book of universes whose first pages were all written in the same fleeting, foundational instant. The most astonishing part of this story is not just that it happened, but that it happened in a way that led to us. Every step we have traced, from the breaking of symmetries to the 1 in a billion surplus of matter, depended on the exact values of nature's fundamental constants. The strength of gravity, the mass of the electron, the precise energy of the Higgs field. These numbers are not predicted by any theory, they are simply measured. And if any one of them had been even slightly different in that first microsecond, the cosmic outcome would have been unrecognizable. A slightly stronger strong nuclear force, and all hydrogen would have fused into heavier elements instantly, leaving no fuel for stars. A slightly weaker electromagnetic force, and atoms could not form stable bonds, preventing chemistry and molecules. This apparent fine-tuning leads to a profound and sometimes controversial question, known as the anthropic principle. In its simplest form, it states that the universe we observe must be compatible with the existence of conscious observers like ourselves. It is not a theory that explains why the constants are what they are, but a framework for asking the question. From a scientific perspective, it shifts the inquiry. Instead of asking why the constants are tuned for life, we can ask what physical processes in the first microsecond could have set these values. Was it a random, singular event, a cosmic lottery ticket we happened to win? Or does it point to a deeper structure, perhaps a multiverse where countless universes with different constants exist, and we naturally find ourselves in one of the rare ones capable of generating stars and planets? Investigating the first microsecond, then, becomes more than a historical reconstruction of particle physics. It is a direct investigation into the preconditions for our own reality. By understanding the mechanisms that set the rules, from the decay of the Inflaton field to the freezing out of dark matter, we are not just learning about the past. We are asking the most fundamental question of all: why does a universe that began in a state of pure, symmetric energy evolve into a complex, structured, and life-permitting cosmos? The search for those answers, written into the fabric of reality in that first fleeting moment, is ultimately a search for our own cosmic context. The quest to understand our cosmic origin does more than satisfy curiosity. It fundamentally reshapes our world. The monumental machines built to peer into the first microsecond are not just scientific instruments, they are engines of innovation, pushing the very limits of engineering and computing. To recreate the conditions of the primordial universe, we must first master technologies that once seemed like science fiction. Consider the powerful superconducting magnets that steer particles at nearly the speed of light inside the Large Hadron Collider. Operating these magnets requires cooling them to a temperature colder than the void of outer space, a feat of cryogenics that drives advancements in materials science and energy efficiency with applications far beyond the laboratory. The staggering amount of data generated by a single collision is another frontier. Each year, these experiments produce data equivalent to hundreds of thousands of high-definition movies. Managing, processing, and sharing this deluge of information gave birth to the worldwide computing grid, a pioneering global network that distributes processing tasks across thousands of computers in dozens of countries. This grid computing model, developed to handle cosmic data, paved the way for the vast, distributed cloud computing systems that now power modern business, communication, and research. The pursuit of the universe's first moment has, in very tangible ways, accelerated the development of the digital infrastructure that connects our world today. Perhaps the most profound human achievement in this quest is not a technology, but a testament to our collective potential. Building and operating a machine like the Large Hadron Collider is a monumental feat of global cooperation. It is not owned by a single nation or corporation, but by a consortium of over 20 member states, with thousands of scientists and engineers from more than 100 countries contributing to its design, construction, and daily operation. This international laboratory is a unique space where borders dissolve in the shared pursuit of a common goal, understanding the fundamental rules of nature. Researchers from nations with complex political relationships work side by side, sharing data and insights with unprecedented openness. The World Wide Web itself was invented at CERN to help these global teams collaborate, a tool born from the need for scientists to communicate seamlessly across continents. This spirit of open collaboration extends to the data itself, with findings made publicly available to researchers everywhere, fostering a truly global scientific community. In an age often defined by division, these projects stand as powerful reminders of what humanity can accomplish when we unite around a shared, awe-inspiring question. The drive to comprehend a microsecond of ancient time has, in the present day, woven a web of human connection, proving that our greatest discoveries are not just about the cosmos, but about our own capacity to work together. So let us gather the entire journey into a single, breathtaking timeline. From the absolute beginning to the formation of the first stable particles, the first microsecond unfolds in a sequence of transformative leaps, each one setting the stage for the next. At time zero, the universe emerges from the unknowable singularity of the Big Bang. For the first 10 to the negative 43 seconds during the Planck epoch, the cosmos is a realm of such extreme energy that space and time themselves are born from a quantum foam, a frontier beyond our current physics. As we move forward from 10 to the negative 43 to 10 to the negative 36 seconds, the universe enters the grand unification epoch. Here, three of the four fundamental forces, the strong, weak, and electromagnetic, are fused into one symmetric superforce, a state of perfect, elegant unity. This symmetry is shattered around 10 to the negative 36 seconds, triggering cosmic inflation. For a mere sliver of time, until about 10 to the negative 32 seconds, space itself undergoes exponential expansion, stretching by a factor of at least 10 to the power of 26. This violent growth spurt smooths and flattens the cosmos and magnifies quantum ripples into the seeds of all future structure. When inflation ends, its energy is dumped back into the universe in a process called reheating, igniting the hot Big Bang in earnest and filling the cosmos with a searing, primordial Quark-Gluon Plasma. For the next several microseconds, this is the state of everything, a dense, opaque soup where quarks and gluons roam free. Then, as the temperature falls below 2 trillion Kelvin, the strong force activates in an event called hadronization. Quarks and gluons are permanently confined, snapping together to form the first protons and neutrons. By the time the clock reads 1/millionth of a second, the universe has transitioned from a unified symmetry to a structured arena, from pure energy to the first tangible seeds of matter, all while laying down the gravitational blueprint for galaxies that would not form for billions of years. Every event in this sequence is a direct cause for the next, a domino chain of cosmic evolution that turned a spark of potential into the foundation for everything we know. This remarkable convergence of evidence forms the bedrock of our modern cosmic story. We have not one, but several independent witnesses to the events of that first microsecond, and their testimonies align with stunning precision. From the depths of particle colliders, we extract direct, experimental proof of the Quark-Gluon Plasma and the behavior of matter under those extreme conditions. This is our laboratory recreation, a controlled glimpse into the primordial fire. Then we look to the sky. The cosmic microwave background provides a fossilized imprint of the universe's infancy, its smoothness and specific pattern of ripples offering undeniable support for a period of rapid inflation and the quantum origins of structure. When we map the present-day cosmic web of galaxies, we are reading a later chapter of that same story, seeing how those initial ripples grew under gravity over billions of years. The statistical properties of this vast architecture match in exquisite detail the predictions derived from those first quantum seeds. Finally, the elegant mathematics of particle physics and general relativity provides the theoretical framework that binds it all together, predicting the sequence of symmetry breaking and phase transitions that had to occur. It is a detective story of the highest order, where clues from the unimaginably small, the ancient, and the astronomically large all point to the same sequence of events. Of course, mysteries remain. The true nature of the Inflaton field, the details of reheating, and the complete picture of grand unification are still active frontiers of research. Yet the broad outline from a hot, dense beginning through inflation and the formation of the first particles stands as one of the greatest achievements of the human intellect. We have pieced together a coherent narrative of creation from fragments of light, showers of particles, and the deep language of mathematics, constructing a history of a time before time itself had any meaning. The story of that first microsecond is a chain reaction of cosmic decisions. It was not one singular bang, but a rapid-fire sequence of phase transitions, each one locking in a new rule of reality. Symmetries broke, forces separated, and particles gained mass and identity, all within a span of time too brief for any clock to measure. This cascade established the fundamental ingredients and the governing laws for everything that would follow, from the first atom to the spiral arm of a galaxy. That we can speak with such confidence about events so ancient and inaccessible is a testament to a profound partnership, the marriage of human curiosity with relentless ingenuity. Theoretical physicists provided the elegant mathematical narrative, a story written in the language of fields and forces. Experimental scientists then built the monumental machines to test that story, recreating fragments of the primordial fire to see if the equations held true. It is a dialogue between imagination and evidence, spanning from the blackboard to the underground collider and out to the farthest reaches of observable space. This collaborative endeavor has given us a coherent origin story, a scientific creation myth built not on faith, but on reproducible observation and predictive power. Yet the final chapter is far from written. The next generation of experiments awaits, from more sensitive observatories mapping the cosmic microwave background in finer detail to ambitious new colliders designed to probe even higher energies. Each new instrument is a sharper lens turned toward the dawn of time, promising to refine our story, challenge our assumptions, and perhaps reveal entirely new layers of the cosmic prologue. The quest to understand our ultimate beginning continues, an unfolding mystery that invites us all to look deeper. If you found this journey from quantum ripples to cosmic structure compelling, be sure to subscribe. Our channel is dedicated to exploring the grandest puzzles of the cosmos, from the nature of dark matter to the fate of the universe itself. Join us as we keep unraveling the secrets written in the stars and in the first fleeting moments of everything.